Okay, in this video we're going to talk about the name of the language that is accepted by Turing machines, and then we're going to do a linear bounded automata, but we will get into more detail of the hierarchy of languages and automaton in the next module. So I just wanted to tell you the name of the language there that a Turing machine accepts. Of course, a Turing machine can accept a regular language, which we did that for our first examples. But, and you can also create a Turing machine for a context-free language. But the languages that you cannot build an NPDA or a DFA or an NFA for are called recursive enumerable languages. And then a subset of a recursive enumerable language is called a recursive language. And the difference, what sets apart the recursive language is that for every string that you can create from your alphabet, the Turing machine will halt. But a recursive enumerable language will just make sure that it will accept every string that is in the language. So a recursive enumerable language could potentially not halt. But a recursive language, which is a subset of that, will definitely halt no matter what string you create out of the alphabet. All right, so now let's talk about a limited Turing machine. A limited Turing machine is called a linear bounded automata. And a linear bounded automata, you will restrict the way that you use the tape. You can use only the part of the tape that is occupied by the input. So let's go to some details about an LBA, or linear bounded automata. Okay, you take a Turing machine and you restrict the limit of the tape that can be used. That's the input part of the tape. That's actually the example that we already did. We already did that restriction. Same thing, that's what I just said. Okay. You can use two special symbols or markers to bracket where the input starts, and you can never go past that. So we do have the blank. So the examples that I showed you, we would start, the tape could actually be infinite in both directions, but if you're doing a language and you're building a linear bounded automata, you cannot go over. So if this is your tape, you have your special symbol here on this side. You could have a special symbol here on this side. So it cannot overwrite the special symbols. So you're limited to this area of your tape. A linear bounded automata are assumed to be non-deterministic and accept languages in the same manner as other Turing machines accept. And it can be shown that any context-free language, you can use a linear bounded automata, so it is above an NPDA, and you could build a linear bounded automata for any context-free language, but you can also build a linear bounded automata for a language that is not context-free. So this right here, this is a language that is not context-free. A to the n, B to the n, C to the n. This is very similar to the Turing machine that we already did in our first example. And we would you would create your LBA the same way by creating some additional alphabet. So I would pick X, Y, and Z. X for the A's, Y for the B's, and Z for the C's. And you do the same way because you need to have the same number. You change this to an X, change this to a B, to a Y, change this to a Z, then you go back, change this to an X, change this to a Y, change this to a Z, go back, X, Y, Z, and then if you can get this special symbol, you have now it is a string that is in that language. So this is just like the other example, and so I'm not going to spend a lot of time on it because I spent a lot of time on, no one's correcting this. I need to correct that myself. I spent a lot of time on it in the last video. All right, so this is an example. We would use 6 states. We don't need to use seven. I mean, we use 7 states. Q6 is going to be our accepting state. We have our alphabet. We have our tape alphabet, which has the extra blank, which is the not part of our alphabet, but is part of our tape alphabet. And here is an example of the LBA, which it's very similar to the other example that we already did, which was A to the N, B to the N, A to the N, B to the N, where N does not equal 0. So I don't think I need to really go through this in detail, but if you have any questions, I just wanted to point out that we are, in this class, we're getting towards the end of the semester. So I did put a couple of examples of Turing machines in your assignment, but the solutions are part of that. So you should be able to look at the assignment, and I will be creating a video based on the assignment 7 with the solutions and talk about some of the Turing machines that are in that assignment. So linear bounded automata are not as powerful as standard Turing machines.